Hi, Dan Fleisch again. And here in Chapter 3 of A Student's Guide to the Schrödinger Equation, we finally get to the Schrödinger Equation. When you first look at this equation, the usefulness of all the mathematical background in Chapters 1 and 2 may not be clear. After all, the Schrödinger equation has a lot in common with other second-order partial differential equations, so why the need for all the rigmarole about abstract vector spaces, bras and kets, and the inner product? The answer to that question has less to do with the form of the Schrödinger equation itself than with the form and meaning of the solutions to the Schrödinger equation, as you'll see in Chapters 4 and 5. But in this chapter, the focus is squarely on the equation and what we can learn by considering each of the terms of that equation. Before examining those individual terms, I try to give you an idea of the origin of the Schrödinger equation in section 3.1. In that section, you'll see that although the Schrödinger equation cannot be rigorously derived from first principles, it is at least consistent with conservation of energy. Specifically, you can get to the Schrödinger equation by writing the total energy as the sum of the kinetic energy plus the potential energy, and then you can use the Planck-Einstein equation to relate energy to frequency and the de Broglie relation to relate momentum to wave number. But the Schrödinger equation includes partial derivatives over time and space, as well as the imaginary unit I. So where do those terms come from? That's also explained in section 3.1, in which the expression for a plane wave can be seen to connect frequency to a time derivative and wave number to a space derivative. It even brings along the required factor of I. So does that mean that the Schrödinger equation applies only to plane waves? Happily, it works for much more than just plane waves, because it's a linear equation, and many different wave functions can be synthesized by superposition. That is, by forming a weighted linear combination of plane waves. So, the Schrödinger equation describes the behavior of a wide variety of wave functions over space and time. You can learn a lot about that behavior just by considering the form of the equation and looking at the meaning of each term. That's exactly what you'll find in section 3.2, a term-by-term description, along with an explanation of what it means for this to be a parabolic, second-order, partial differential equation. You can also see how the Schrödinger equation resembles and differs from other equations, such as the diffusion equation and the wave equation. After that, in section 3.3, you'll see that spatial and time portions of the solutions to the Schrödinger equation are separable, which means that a time-independent version of the equation can be written. The wave function solutions to that very useful time-independent Schrödinger equation can then be combined with a time-dependent factor to yield the full space and time wave function psi of x and t. As you work through the first three sections of this chapter, you may notice that the wave function solutions psi of x and t have only one spatial dimension, x. But we live in a universe with at least three spatial dimensions. So, although you can solve several interesting problems using the 1D version, some problems do require a full 3D treatment. You can read about the three-dimensional version of the Schrödinger equation in section 3.4. And as always, the final section of this chapter is a set of problems that I strongly suggest you try to work before diving into the later chapters. Good luck with that.